All right. Good evening, class.
Good evening, sir.
Yeah,
Yes,
I
sir.
hope you're doing well.
Yeah, we are doing fine, sir.
Yeah,
Yeah,
I'm doing okay, sir.
yeah, I'm also doing very well. So, thank you. Yeah, so we want to begin with our class. So far, we've looked at in the last two lectures, we looked at probability, the concept of probability and probability distribution. Okay, and we said that it was important because outcomes of random experiments, okay, happen with chance, okay, and to predict the possibility of occurrence of, of an outcome, it will be important to study the concepts of probability, okay, so as to understand, first describe the process as well as to make informed predictions, okay, on various processes. Today, we want to move a step further, okay, into what we call as statistical inference, okay, statistical inference. When we began the course, we said statistics is in two folds. The first fold is descriptive statistics, where we're looking at data collection methods. We're looking at organized data organization and data presentation. And the next phase is inferential statistics, where we're looking at analysis of data and inferences of the results we obtained on the population for decision what taking. Okay, good. So we are beginning with a series of statistical, inferential techniques. Okay, and before we do that, there are some few concepts which we need to understand. Okay, which we'll be looking at, and for the next, um, starting from now onwards, we'll be looking at a number of inferential tools which are used for different purposes. Okay, and the first thing we need to understand before we go into statistical inferences will be the concept of sampling what distribution, because now we are going to deal with samples. Okay, all the calculations we did for the mean, for the standard deviations were on, we were assuming that the data was population for the population. Okay, but now we're going to look at samples, the concept of samples. I introduced that to you on day one. Okay, we are going to look at samples and then how to get estimates out of samples, and when to use them and how they are going to be used even in inferential analysis, including um, estimation techniques and hypothesis testing. Good. Now, first, when we talk about statistical inference, okay, we are talking about a process of making a guess, okay, about the truth. The process of making a guess about the truth, okay, using sample information or from a sample observation or data, okay. And then when you see me use truth here, when we talk about truth, truth is the actual occurrence in the world, in the population, the actual, okay, occurrence or the actual, okay, value in what? In the population. So when we talk about truth, we are talking about what? A value, a population parameter, okay? A value that describes okay, an aspect of the population, like the population mean, okay. So Vortic mineral water will claim that their 1.5 liters bottle indeed contains 1.5 liters of water, okay. That is a claim about the all the bottles they produce which are consumed locally and what internationally, okay. That is a claim, a truth. And then the next word we have here is sample, okay. And then we are saying that it is not possible to always observe what the population, okay. We made mention of that too in the second lecture. It's not always possible to examine the entire population because you can't go selecting all the bottles Vortic mineral water produces across Ghana and those that are exported. You can't go, I mean, observing all those bottles. It's not possible, okay, due to time, due to resources, due to feasibility issues. So in investigation, for us as scientists, we make use of samples, okay, which is a section of the population, okay, and then based on the sample data we have, okay, we make guesses regarding what the population, okay. Now we'll be looking at estimation techniques, but two key comparisons we want to do for now, okay, is trying to know the differences between what we refer to as parameters and sample statistics, okay, population parameters and statistic, okay. Now, when we talk about statistic, we don't mean statistic as a science, as a branch of mathematics, but we mean statistic as a value estimated, okay, from sample statistic. Is a value calculated from the sample what observation or the sample data, okay. So sample statistics are calculated from the sample data, okay, whereas population parameters are values that are calculated from the population data, okay. So we saw this notation, which is mu, the mean of the process, from earlier computation, earlier chapters or lessons, okay. And then we also saw the variance, okay, of the population, from I think that was a third lecture, okay. Good. Now in sample statistic, we are going to deal with X bar, which is the sample mean, okay. The sample mean calculated, the formula is almost like the population mean, okay, mu. It is just like the population mean. And the reason why is because the sample mean is an unbiased estimator. We'll get to estimation techniques. It's an unbiased estimator of the population mean. So in other words, when you calculate the sample mean of the data, if the sample was well selected, then that sample mean should be a good estimator for what? For the population mean. So when I use the word estimator, I'm saying an estimate, okay, an estimate. So you don't know the population mean, but if you pick the sample, a number of samples well selected, then when we find the sample mean, it should be a good guess for the population what mean. The same way, we also have the sample variance, okay? The sample variance is slightly different, okay, from the population variance, okay? This time, the denominator is what? N minus 1 instead of n, okay? And then the deviation is from the sample mean. The deviation is not from the population mean. That's the difference we have here. Xi minus what? Mu. For population variance is xi minus mu, but for sample variance it is xi minus what? X bar. of the sample. Okay. So you take note of that. So these two formulas are examples of sample what statistic. Again, we can also have sample statistic like the sample proportion. Okay. So in other words, proportion estimated out of what? The proportion estimated out of what? A sample what? Data. Okay. That can also be what? A sample statistic value. Whilst the proportion itself from the population is what? The population, a population what? Parameter. Okay. So with this understanding, we want to go a bit further, unless somebody has a question for me. Okay. So I have some few examples here. I said sample statistics. They are summaries, summary measures calculated from what? Sample data. Okay. So examples are stated here: the mean, the difference in the means or proportion, odds ratio, correlation coefficient, etc. Okay, then population parameters are the true values we are looking for in the entire world. Population of what? Interest. Okay, very good. Yeah, so these are further examples of sample statistics. Okay, very good. Now, so for example, we have the single sample mean, which we've just looked at, the single sample proportion. Then when we find the difference in the sample means, okay, two sample means, okay, which will eventually give us a test statistic we refer to as a t-test or the z test, okay, the standard normal statistic, okay. Yeah, or when we find a difference in proportions, we use the z-word test. They are all examples of our sample statistics. Now, what we need to understand with sample statistic is the fact that if X, so I'm going to cast our minds back to last week's class, okay, that if the distribution of X is normally distributed with a mean and a variance, okay, sigma square, and then we select some samples from the process X. You see, X is any process, like I told you, okay? So let's assume the process is normally distributed, but other processes could be the waiting time to board a bus or the time it takes in a queue, okay, to be served at the bank, okay? Very good. So if the process is maybe a queuing model and we want to find what arrival rate or the probability of occurrence, okay, then we are dealing with what? A Poisson process, okay, with lambda, okay, as our parameters. You understand? So that will be the process. Now, what we are saying is, if we want to examine the a sample, a selection, maybe within 2 o'clock to 3 o'clock, people come to the bank from morning all the way to around 5 o'clock. But we want to sample, just do a short sample between 2 to 3 o'clock and then see the average waiting time in the bank. Okay, that will be a sampling procedure. Now, if we should sample from the bank, then the occurrences in the bank, okay, will also follow the sample distribution. Okay, will also end up following what from the sample will also end up following what? A Poisson process. Okay, it will also have a distribution of its own. Okay, And the same way, the sample mean of the process will also have a distribution of its own because it's coming from what? The same process. Okay? So if the process is normally distributed, a sample from the process will also be what? Normally distributed. And then the statistic calculated. So statistic, for example, X bar is a statistic calculated from what? X. Okay, the same observation from the process. So X bar, which comes from a normally distributed variable, will also be what? Normally distributed. Good. So what we are saying in summary here is statistic values also follow what? Distributions. Good. But the distribution of a statistic is a theoretical what? Construct. Okay. The distribution of a statistic is a theoretical what? Construct. So for a number, like I said, for a number of processes, okay, there are number of theoretical models which are used in describing the process. So if we are in the bank waiting, then the waiting time follows what? Exponential process. If we are at the game center trying to predict the chance of occurrence, that will be a stochastic model. It will depend on the process. We may be using a Black-Scholes model for prediction. Okay, so every process and follows some distribution, which means that the statistic will also follow a theoretical what? Process. Now, let's just go straight to the point. We don't want to spend too much time here. Okay. Next, we need to understand that what we mean by sampling distribution of a sample mean. Okay. Now the distribution of the sampling distribution of the sample mean, okay, is defined as the distribution using the computed means from all possible random samples of a specific what size are taken from the population. Okay, now let me touch on this briefly. I'll need space for that. So let me touch on the second, the properties, and then I'll explain to you. Then the next point is the mean of, with regards to the properties of the distribution of sample means, the mean of the sample mean, okay, is always equal to the mean of the population what? Mean. That is one rule we must know. Then again, the standard deviation of the sample mean, okay, is always what? Smaller than the standard deviation of the population mean. Okay, specifically, it is the standard deviation of the population mean. So the standard deviation of the sample mean, okay, will always be equal to the standard deviation of the population over the square root of the sample size. So it's always going to be smaller. The standard deviation of the sample mean is always going to be smaller than the standard deviation of the actual population's standard deviation. Okay, let's try and demonstrate this briefly before we proceed. Just a minute. Okay. Yeah, so I'm going to do a little demonstration. I have a population here. Okay, let's say in my class, I had 3 students. who were Kojo, who scored, let's say 3/5 in exams. And then I have Ama, who scored 4/5. And then I have somebody else, okay, Wisdom, who scored 5/5 in examination. Now, like I said, in this case, the population is made up of just 3 people. There were only 3 students in my class. But assuming I wanted to sample, okay, I wanted a sample of two people. Then the possible samples I could have will be what? The possible samples I will have. So these are the samples. The possible samples I will have will be for Kojo and Ama, which will be 3, 4, 3, Kojo and Wisdom. You see, I'm selecting samples of 2. And then I could also have Ama and Wisdom, okay, as my sample. So I have 3 possible samples. These are all the possible combinations I could have. Good. Then when we calculate the statistic, which is what? X bar, okay? The sample mean will be what? 3.5. That is 7 divided by 2. Then for this, 3 plus 5 will be 8. Divided by 2 will be what? 4. Then for this, that's 4 plus 5. 9 divided by 2 will be 4.5. Okay. Now, I want to find the mean of the sample mean, which is property 1, okay? The mean of the sample mean. Good. Now, the mean of the sample mean will be equal to what? 3.5 plus 4 plus 4.5 over 3, which will give me what? Which will give me 4. And I'm sure by now you have your calculators by you. If you don't have, try and grab your calculators, because we have a lot to do today. Good. Now, let's also go back to the population and then estimate the population mean. So the population mean would have been what? 3 plus 4 plus what? Plus 5. Okay, divided by 3. And again, this will be what? 7 plus 5, which is 12. 12 divided by 3 is what? 4. So you can see that as a principle, the mean of all possible sample means, which is of the sampling distribution, okay, will be equal to what? The mean of the population. Good. That is the first rule. So the mean of the sampling means will be equal to what? The mean of the population. And then again, that can also be verified, okay? The standard deviation, or if you like, let me put it this way, the variance of X bar, the variance of the sample mean, is equals to the variance of the population over N, okay? And then if you want the standard deviation, you find the square root of both sides. That is why in the first case, it was sigma over the square root of N. Okay, so these are two very important words, two very important properties of the sampling distribution we need to know. Good. If you have any questions, you can ask whilst we move along. Okay. So in summary, we are saying that if X, the sum in general, the sample mean X bar is said to follow a normal distribution with a mean mu and a variance what? Sigma squared over n. Okay. So we can write S bar also to be normally distributed as long as X was also what? Normally distributed. Okay. Then if the distribution is unknown, you see, if a distribution is unknown, last week I did mention that one relevance of the normal distribution is when a process goes on over and over and over and over, regardless of where the process is taking place, it becomes what? Normal. A very simple understanding. If you get to the bank today and you estimate the average waiting time in the queue for you as 15 minutes. Okay, that is an exponential process. But if you keep going to the same bank after 2 years, every day you go to the bank, after even 300 days at the bank, okay, you know that it is just normal, okay, for you to have your expected mean to be what? 15 minutes. So eventually an exponential process or exponential model can be easily modeled using what? The normal process. Okay. Now, a very interesting theorem helps us to achieve this. And we call that theorem the central limit theorem. The central limit theorem is basically saying the same thing, that as your process gets large, or as the number of observations gets large, then all distributions will approximate to a normal distribution or to a normal process. Okay, so we are saying that if the population distribution is unknown, then the central limit theorem, which is the CLT, guarantees that the sampling distribution of X bar will also approach normal distribution with a mean of mu and a variance of what? Sigma squared over n. Okay, as long as the sample size is what? Large enough. So if your sample size is large enough, then regardless of where X bar is coming from, we can say that it is per the CLT that it approximates towards a normal process. Okay, and its mean will be approximately equal to the mean of the process, and the variance will also be, close to the variance of what? Sigma squared over n. Okay, let's continue. So these are very important theories, knowledge we need to know, okay, before we move into any inference. Now, the next thing we have to know is if that is the case, okay, if that is the case, then we can also infer that if X is normally distributed with a mean of mu and a variance of sigma squared, and X can be standardized as, okay, from last week's class, if we can standardize X as what? The value of the process or the observation X minus what? The observation for X, sorry, minus the mean of the process over the standard deviation. Then we can also say that if X bar is normally distributed with a mean of what? Mu of X bar, okay? And then a variance of what? Sigma square of X bar, right? Now, before I standardize, let me rewrite this same statement because we've looked at two important properties. We want to apply it. So that is X bar then is also normally distributed with a mean as the mean of the population, because we said the mean of X bar, the sampling mean, is equals to the mean of the population. And we also said that the mean, the variance of the sampling mean is equals to the variance of the population divided by the sample size n. So if that is the case, then we can also standardize X bar into Z's, okay? We can write X bar into Z's by subtracting the mean, okay, from the observed X bar value, okay, which will be like this. So it will be X bar minus the mean here over a standard deviation, okay? So the standard deviation, if you like, this can be written like that. X bar Z is equals to S bar minus mu over what? The square root of what? Sigma squared over n, okay? And of course, once you find the square root of sigma squared, this will be sigma, and then the denominator will be square root of what? N, okay? That is why we are having X bar minus mu over sigma divided by the square root of n. So what we are saying is, if X bar is normally distributed with mean of mu and variance of sigma squared over n, then X bar can also be standardized, okay, using into the Z statistic, okay, as what? S bar minus mu over sigma divided by the square root of n. Okay, so these are very exciting theories. I'll pause here and take one or two questions from you if you have any before we continue. Any questions?
No question, sir.
Okay, very well. Then let's continue. We want to take some examples to demonstrate these theories. So we have an example here. He says that suppose that a random sample of size n equals to 36 is chosen from a normally distributed population. So it means the sample is from a normal distributed population, which means that the sample is also going to be normally distributed. Okay. And then we've been told that normally distributed population with a mean of this. So this is the mean of the population, mu. And the variance of the population, sigma squared, is what? 400. And we are asked to determine the probability that the sample mean will be greater than what? 205, okay? Will be greater than 205. Okay, so this is quite simple. So we are saying that We want to find the probability that X bar, the sample mean, will be greater than what? 205. So this is just an extension of what we did in the last class. Okay, so first we have to standardize. And in standardizing, like we said, to change to Z, it will mean subtracting the mean of the population, which is mu 200, and then dividing through by the standard deviation of, okay, let me write that here. So Z is what? It's X bar, okay, minus mu over what? Sigma over the square root of n, okay? Take note of that. It's no more sigma. So first you find the square root of variance is 400. Variance is 400. Okay. So you need to find the square root, which will be equal to what? Which will be equal to 20. Okay, so sigma is 20. Okay. So we are going to have what? 20 over the square root of n. N is what? 36. So over the square root of what? 36. This should give us P into bracket what? Z, which is greater than 5 over, this will be 6. Square root of 6 will be what? Of 36 will be what? Will be 6. Okay. And then 20 over 6. Okay. So we got 20 over 6 here. Or if we change that, that will be this divided by that. So that will be what? This, I'm trying to write this. Okay, because of the division, it will be divided by 20 over what? Over 6. Okay, so then we can also write that as 6 over 20 times 6 over 20. That's what I mean. Good. So this can equally be written as what? 5 times what? 6 over 20, which will be 30 over what? 20, right? 30 over 20. 30 over 20 is the same as what? 3 over 2, which is what? 1.5. Okay, good. So which means that then we can write